Every second, the national power grid delivers into your home an amount of energy strong enough to be dangerous with a single wrong touch. Yet, through nothing more than a small plastic box, a charger, that same current is reduced to something so gentle that a silicon chip thinner than a human hair can operate safely. This raises a simple but crucial question. How can such a tiny device teach electrons microscopic particles that naturally move in chaotic, unpredictable ways to behave, to flow in the right direction, at the right level, and at the right speed? Every second, the electrical grid feeds your home with a powerful current that can become hazardous if handled incorrectly. What is remarkable is that this entire flow of energy, after passing through roughly 10 centimeters of plastic, metal, and printed circuits, emerges as a small, extremely stable current capable of sustaining chips thinner than a strand of hair. There is no magic involved, only engineering. And that engineering works by forcing electrons particles that normally move in erratic and difficult-to-predict patterns to obey strict voltage conditions demanded by electronic devices. A charger is the intermediary that transforms the grid's large, fluctuating, and coarse electrical supply into a small, precise, direct current. To understand how this transformation happens, we must follow 4 consecutive mechanisms converting AC to DC. Smoothing the voltage, stepping it down using high-frequency switching, and finally isolating 2 voltage domains using light. Electricity from a wall outlet is alternating current, or AC. This means the voltage does not remain constant but continuously rises and falls, reversing direction about 50 to 60 times per second. Electrons inside the wire do not travel steadily from the power plant to your device. Instead, they oscillate back and forth around an average position. This behavior makes AC ideal for long-distance transmission, because power stations can efficiently step voltages up or down, allowing electricity to travel hundreds of kilometers with minimal loss. However, this oscillating nature also makes AC unusable for electronic devices. Processors and logic circuits require a voltage that flows in one direction and remains almost perfectly stable. If AC were fed directly into a chip, the constantly changing voltage would introduce noise, causing malfunction or permanent damage. Therefore, the charger's first task is to convert this constantly varying current into direct current DC, the form of electricity that electronic components can tolerate. This is the first step in taming electrons, to convert AC into DC. And chargers use diode. A diode behaves like a one-way gate. Current can pass through in one direction but is blocked in the opposite direction. When 4 diodes are arranged in a bridge rectifier, they create a mechanism that ensures that, regardless of how the AC input reverses direction, the current leaving the rectifier always flows in a single direction. The result is direct current, but this DC is still unstable. Its voltage rises and falls in rhythm with the original AC waveform, much like a heartbeat that constantly surges and dips. To smooth this voltage, a large capacitor is placed immediately after the rectifier. A capacitor temporarily stores energy when the voltage rises and releases it when the voltage drops, acting like a small reservoir that evens out the flow. This makes the voltage far smoother, closer to true DC. Even so, the voltage at this stage remains extremely high, often exceeding 300 volts. After rectification, electronic devices require only a few volts, which means the charger must reduce the voltage further, precisely and safely. This is where high-frequency switching enters the picture. Instead of using large, heavy iron transformers like older designs, modern chargers rely on switched-mode power supplies, or SMPS. The operating principle of an SMPS is fundamentally different. Rather than reducing voltage continuously, it chops the current into square pulses by rapidly turning an electronic switch, typically a transistor, on and off, sometimes tens of thousands of times per second. Once the current is divided into these high-frequency pulses, A small transformer operating at high frequency can easily step the voltage down to the desired level. By adjusting how long the transistor remains on relative to how long it stays off, the control circuit can precisely regulate how much energy is transferred to the output side. When the device needs more power, the pulses are lengthened. When it needs less, the pulses are shortened. This adjustment happens continuously and extremely fast, allowing the output voltage to remain stable even as power demand changes. This is why modern chargers can be both compact and powerful at the same time. Yet one critical challenge remains. The low-voltage control circuitry must be completely isolated from the high-voltage power section to ensure safety. To keep these two voltage domains from ever touching, chargers use optical isolation. The key component is an optoiolator, which contains two internal parts, a tiny LED and a light sensor. The LED sits in the low-voltage region, while the sensor resides in the high-voltage region. When the output voltage changes, the low-voltage circuit adjusts the brightness of the LED. This light crosses an insulating gap and is detected by the sensor, which then regulates the power side control accordingly. Crucially, light passes through, but electrons do not. The two voltage regions remain physically separated, ensuring that any fault on the high-voltage side can never reach the low-voltage side. This is the charger's final layer of protection, safeguarding both the device and the user. A compact charger is, in reality, a carefully orchestrated system of multiple engineering mechanisms. It transforms a powerful, fluctuating electrical supply into a stable and safe current by forcing electrons to move in one direction, smoothing voltage, stepping it down with high-frequency pulses, and finally isolating voltage domains using light. All of this occurs within just a few centimeters of circuitry and material. Yet it is enough to ensure that the most delicate electronic devices can operate reliably every single day.